So we've talked about carbon dioxide quite a bit and how they link to fossil fuels. But what we haven't really talked about is this idea of greenhouse gases, which is what really is kind of the crux of climate change. It's really the most important thing or most important aspect to focus on when it comes to climate change. But we haven't talked about those at all. So now what I'm going to do is kind of make that connection between the carbon cycle and how that relates to greenhouse gases, which then relates to climate change. So I talked a lot about carbon dioxide, the CO2. And I talked about how it's getting in the atmosphere from fossil fuels when we burn them. But the question is why does that matter? Like, okay, there's carbon dioxide already in our atmosphere. You and I exhale carbon dioxide. So why does this matter? Well, the big reason why this matters is because carbon dioxide is a greenhouse gas. And that's really, 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 really important because this greenhouse gas is going to give us different effects here on Earth. So let me kind of explain how greenhouse gases work. So there's something around Earth, or this theorem, or not even theorem, but a principle called the greenhouse effect. And this is something that's naturally occurring on Earth. It's not like this is a new thing. And so what the greenhouse effect is here we have the sun, and the sun is giving off lots and lots of solar energy. And so that solar energy is coming in and coming in. Some of it comes in and gets absorbed by our atmosphere. Some of it comes in and lands on Earth, where it's used for photosynthesis, where it's used for a light source. And really, more importantly, what happens is that solar energy, that light energy, will get converted into heat energy. And so that's why during the day it's warmer than it is at night because of that conversion. Now, once that heat energy gets transformed, or once that light energy gets transformed into heat energy, the heat doesn't just stay there. Some things that can happen with that heat and with that energy is it kind of bounces off the Earth's surface, so to speak, and it goes back through the atmosphere and it'll get re-emitted into space. For example, the space, like literally outer space around Earth, is much warmer than not around Earth. So it's literally warming up the space around us. The other thing that can happen is here's that solar energy that gets turned into heat energy that goes back into the atmosphere, but then it hits something. And it literally hits it and bounces it back to Earth, like you see here. And from there, it might get bounced back, trying to go back into space, and then get bounced back again, coming back into Earth. So it's almost like this pinball machine where this piece of energy is trying to go back into space, but it's getting bounced back towards Earth. Now that thing that solar energy is hitting is a greenhouse gas, is a molecule of a greenhouse gas. So for example, carbon dioxide. There's carbon dioxide all in our atmosphere, and then what happens is that heat energy goes, and it hits that carbon dioxide molecule, and it bounces back to Earth. I like to think of our greenhouse gases, so carbon dioxide is not the only one. We'll talk about that more in just a moment. I like to think of our greenhouse gases like a sweater. When you have a sweater on, the heat leaves your body, so your body's generating that heat. It's trying to leave, go into space, so to speak, but your sweater, your jacket, your blanket is literally bouncing that heat back to your body. The blanket itself isn't generating heat. The blanket is just there as a barrier to trap that heat against your body. So greenhouse gases are the same thing. But this is also where the problem comes, because we're increasing the amount of greenhouse gases in our atmosphere. So essentially what that means is we're putting on another sweater, we're putting on another blanket. Earth is still releasing the same amount of heat, but the problem is that we're trapping more and more of it back to Earth. And that's where a lot of the issues of climate change comes from. Now again, the greenhouse effect has been around literally for billions of years. As Earth's atmosphere developed, so did our greenhouse effect. And it's actually critically important. The greenhouse effect in general is a really great thing. Without the greenhouse effect, Earth would get too hot and too cold that it actually would not be survivable and that we wouldn't have life, or we would have life in very, very primitive forms. At night, it would get so freezing that more than likely Earth would actually probably have larger ice sheets than we currently do. So the greenhouse effect is the reason why we have life on Earth. The issue being we're getting more and more of those greenhouse gases, enhancing that greenhouse effect, and it's not coming with really good consequences. Now what's popping up, the video that'll pop up in just a moment, is a really cool animation that kind of explains this concept of a greenhouse effect better. It also shows you kind of on the chemical side how greenhouse gases are greenhouse gases. Not every gas in our atmosphere is a greenhouse gas. Actually, quite a minority of them are greenhouse gases. So this video kind of shows like how those work. I will not test you on what type of molecule is a greenhouse gas and why. But it is a really good graphic. So go ahead, pause here, take a look at this video, and then come on back. So as I mentioned before, there's actually quite a few different greenhouse gases, or GHGs, in our atmosphere. But despite there being quite a few different types of greenhouse gases, they make up a very small minority of our gases that exist. So here I have a list of 4. There's actually more greenhouse gases than this, but we're really only going to talk about a couple of these. I also have these in order, from the most abundant in our atmosphere to the least abundant. And again, there are more, but they would be 5, 6, 7, 8, etc. down that list. So the very first one's water vapor. Water is an amazing greenhouse gas. You guys actually know this. Think about a summer day, especially here in Maryland, and it's hot, and it's humid. Well, humidity is water vapor, and when it's humid, it feels a whole lot warmer outside than if it was really dry. If you've ever traveled out west, you also know this. It can be a 90-degree day and feels great because it's not humid. So water vapor is really, really good at trapping gases. But the reason you don't hear news reports saying, oh, water vapor is getting so high in our atmosphere, we're all going to die, is because there's a cap. You know this. It's 100% humidity. It doesn't go higher than that. Our atmosphere can hold but so much water. The other thing too with water vapor is that if we were trying to go over 100% humidity, it rains. That water leaves the atmosphere. So water vapor is kind of like a small term greenhouse gas. It's also relative around the world. Some areas have very little water vapor. Other areas have a lot of water vapor. But there's mechanisms in place that if there's too much water vapor in our atmosphere, it rains. So you don't really hear water vapor being talked as a greenhouse gas, mainly because we're not really adding to it and nature has a way of getting rid of it in our atmosphere. However, the same can't be said for carbon dioxide, for methane, for nitrous oxide. These are all gases. And these gases can continue and continue and continue to accumulate in our atmosphere, and nature doesn't really have a way of taking it out. There are some processes, but it's not like it rains carbon dioxide or rains methane. Thank God for that. But there's not really a correction in place like there is for water vapor. So let's take a look at these graphs real quick. So here on the left, the blue pie chart is looking at our air. When you guys breathe, what are you breathing in? So majority of the gases we are breathing are nitrogen, which make up about 3/4, oxygen, which makes up about 1/4, argon, which is about 1%, and then 0.1% is other stuff. Now I'll tell you right now, these 3, nitrogen, oxygen, and argon, are not greenhouse gases. They don't bounce heat back to the atmosphere. So that's incredible, is that a majority of our atmosphere is not greenhouse gases. Our greenhouse gases are actually a really, really small part of our atmosphere. And despite being a really small part, they've actually warmed up Earth so that it's survivable. So these greenhouse gases are really good at doing their job. It's not like half of our atmosphere is filled with greenhouse gases. It's actually a really, really, really small proportion. However, that's kind of the downside too, because every time we add carbon dioxide, we are changing the amount of greenhouse gases, and we're increasing it quite a bit because there wasn't that much to begin with. In red, this is a breakdown of these trace gases. So looking at that composition, a majority of it is carbon dioxide. So a greenhouse gas makes up a majority of these trace gases. There's some other gases in here, but I just want to show you, here's methane. So methane is the 3rd most abundant greenhouse gas in our atmosphere, but you can see it's actually a very, very, very small proportion of our atmosphere and even of our trace gases. Same with nitrous oxide, very, very small proportion of our atmosphere. So although you will hear people talk about nitrous oxide and methane, they don't focus on it horribly much. And the reason for that is just there's not that much to begin with, and we're also not releasing that much either. So I do expect you to know this list, and be sure to know the order of this list. That water vapor is the #1 greenhouse gas, but also keep in mind why we don't really worry about it too much. Here's another graph. I have tons of graphs for you guys today. So I went through all sorts of different sources and found some really great information that kind of explains things that are going on. Now, not all greenhouse gases are created equal. I'm going to emphasize that. Some greenhouse gases are better at being a greenhouse gas than others. Some of them bounce back heat a lot more efficiently and a lot more effectively than other gases. And that's what this graph is showing you. So this graph is what we refer to as normalized. And it's normalized as a global warming potential. And that's what you see up here, this GWP. And it's over a 100-year time span, meaning that over the course of 100 years, like how much, how good of a greenhouse gas is it? Now, carbon dioxide is actually the least efficient greenhouse gas, which is kind of good because that's what we have the most of. So carbon dioxide is okay. It is a greenhouse gas. It bounces back some heat, but it's really not that much. But all of these other ones on this list are compared to carbon dioxide. So for example, and this is probably the most important one that I'm going to share with you, so definitely write this down. Methane, and we'll talk about methane quite a bit as a greenhouse gas, is 28 times more potent, is 28 times better at being a greenhouse gas than carbon dioxide is. So pretty potent. I mean, 28 times more, like that's 28 more times that greenhouse effect. So this is really incredibly important because even though it is less in our atmosphere, it is stronger in our atmosphere. These are also some other greenhouse gases. So we have a lot of FCs. These are fluorinated carbons. We also have nitrous oxide. Nitrous oxide was number 4. But showing you some of these chemicals, like SF6, this is sulfur hexafluoride, 23,500 times more potent than carbon dioxide is. Fortunately, the amount of this in our atmosphere is so incredibly small. So although that is really alarming and kind of scary, it's okay. There's really not that much of it in our atmosphere. But methane, being the 3rd most abundant greenhouse gas, you should know that it's 28 times more potent. And this is also something just to keep in the back of your mind as well, is that not all greenhouse gases are the same. They do fluctuate and they are different from one another. They all have the same function. They all have the same function. However, some of them are better at those functions than others. So this graph is keeping in those global warming potential factors in mind. That carbon dioxide is 1, methane is 28 times, nitrous oxide is 250 times. This is a graph showing how much greenhouse gas emissions there are over the entire world over time. Now it's showing the different gases. So here's carbon dioxide, methane, nitrous oxide, and some of those other fluorinated carbon gases. And this is showing us the global warming potential. So we didn't release 5 millimolecules of methane. We released a lot less than that, but then the people who made this graph times those values times 28 to represent that, yes, we didn't release that much methane, but hey, methane is a lot more stronger, is a lot more potent than carbon dioxide. Same with this nitrous oxide, same with these fluorinated carbon gases. These are with those warming factors in mind. So these have already been multiplied by everything. Despite the fact that all of the other greenhouse gases are a lot more stronger than carbon dioxide, you can see the amount of carbon dioxide that's been released into the atmosphere dwarfs all the other gases. So even though it's not as potent, it's still a greenhouse gas and is being released the most in our atmosphere. Whereas the other greenhouse gases have barely been increasing and are still at a very, very low level. So if you ever hear someone saying, oh, well, we all focus on carbon dioxide, but what about these guys? I'm not trying to say those guys aren't as important, but they're not really the problem, at least right now. Right now, it's carbon dioxide. And as you can see, it's increasing quite a bit and quite rapidly.